Welcome to this lecture on Riemann integration. Today, we are going to explore a fascinating concept known as the equivalence of integrability definitions. If you have ever wondered how mathematicians can be absolutely certain about the area under a complex curve, you are in the right place. We will build this understanding from the ground up. So let us dive right in. Before we look at any equations, let us understand why this concept matters. Imagine trying to measure the exact area of an irregularly shaped swimming pool. You could use square tiles, placing them strictly inside to get a guaranteed underestimate, and then covering the edges to get an overestimate. As the tiles get smaller, the true area is revealed. Alternatively, you could drop a measuring stick at random spots in a grid and add up the volumes. The beautiful truth of calculus is that both physical approaches yield the exact same answer. Now that we understand the physical intuition, let us define these two methods mathematically. The first method, using guaranteed underestimates and overestimates, is called Darboux integrability. It relies on finding the absolute lowest and highest points in any given slice of our interval. The second method, using random measuring sticks, is called Riemann integrability. Instead of seeking extremes, it simply picks a random sample point, or tag, inside each slice. Our goal is to prove that these two seemingly different strategies are mathematically equivalent. This brings us to the core mathematical relationship that connects these two methods. Conceptually, this formula shows that a random sample is always trapped between the worst-case minimum and the best-case maximum. Let us look at the symbols. Capital L represents the lower Darboux sum, which is our guaranteed underestimate. Capital S represents the Riemann sum, built from our random tags. Finally, capital U represents the upper Darboux sum, our guaranteed overestimate. If the lower and upper bounds crush together, the Riemann sum in the middle is forced to equal that exact same value. Before we prove this relationship, let us see it in action with a concrete example. We are given the simplest possible function, a flat horizontal line where the height is always 5. And we want to find the area from 0 to 2. We start by slicing this interval into n equal pieces. Because the total width is 2, each slice has a width of 2 divided by n. Since the line is perfectly flat, it never goes up or down, meaning the absolute lowest point and highest point in any slice are both exactly 5. Continuing with our constant function, we now calculate the actual sums. For the lower Darboux sum, we multiply our minimum height of 5 by our slice width of 2 over n and add them up n times. The n terms cancel out, leaving us with exactly 10. Now, what if we use the Riemann method? No matter where we place our random tag inside the slice, the height is always 5. Plugging this into the Riemann sum formula gives us the exact same calculation. Physically, this proves that for a flat line, both methods yield an area of 10. Now that we have seen a flat line, let us look at a slightly more complex function to see how Riemann sums can collapse into Darboux sums. Consider the straight diagonal line where the height equals x on the interval from 0 to 1. We slice the interval into n equal pieces, so each slice has a width of 1 over n. Because the line is constantly moving upwards, the highest point in any slice will always occur at its rightmost edge, which is located at the coordinate I divided by n. Following up on our diagonal line, we can write out the upper Darboux sum using our maximum height of I over n. Now, suppose we are calculating a Riemann sum, and we deliberately choose the right endpoint of the slice as our random tag. The height of our random Riemann rectangle becomes I over n. When we write out the Riemann sum, we see it is completely identical to the upper Darboux sum. This physically demonstrates that Darboux sums are just special, extreme cases of Riemann sums. So we have successfully used these formulas in concrete examples. This brings us to the formal proof of why this equivalence always holds. using the sandwich theorem. We are setting out to prove that the Riemann sum is permanently trapped between the Darboux sums. We start by looking at just one single subinterval, a small slice of our total area. Inside this slice, the function has an absolute lowest value, an absolute highest value, and a value at a randomly chosen tag point. Logically, the height at the random tag can never be lower than the absolute minimum, and it can never be higher than the absolute maximum. Building on that logical statement for a single slice, we now need to turn these heights into areas. We do this mathematically by multiplying our entire inequality by the width of the slice, delta x sub I. The left term becomes the area of the lower rectangle. The middle becomes the area of the random Riemann rectangle. And the right becomes the area of the upper rectangle. This proves that for any single slice, the random rectangle is physically trapped. To find the total area, we simply sum up these rectangles from the first slice to the last slice across the entire interval. Now we finalize our derivation by writing out the complete sum. We have the total sum of all lower rectangles on the left, the total sum of all Riemann rectangles in the middle, and the total sum of all upper rectangles on the right. By substituting our formal notation, we arrive at our final inequality. This proves that no matter how you slice the interval or where you place your tags, the Riemann sum is permanently sandwiched. If the function is Darboux integrable, the outer bounds crush together, forcing the Riemann sum to converge to that exact same number. To make this mathematical sandwich perfectly clear, let us look at it visually. On the screen, you see a single slice of our interval on the x-axis. The blue rectangle represents our lower Darboux sum, stopping at the lowest point of the curve. The red rectangle represents the upper Darboux sum, reaching all the way to the highest point. Trapped right in between them is the green Riemann rectangle, generated by our random tag point. This diagram beautifully illustrates what we just proved. The random green area will always be taller than or equal to the blue area and shorter than or equal to the red area. Now that we have proven this equivalence, you might wonder why we need both definitions. Understanding this is incredibly important in both pure mathematics and applied computer science. In pure mathematics, dealing with random tag points is messy, so Darboux sums are much cleaner for writing rigorous proofs. On the other hand, finding absolute maximums is computationally expensive for a computer. It is much faster to program a computer to just pick the midpoint of each slice, which is a Riemann sum. The equivalence theorem is the bridge that guarantees the easy-to-program Riemann method will yield the exact same rigorous result proven by theorists. Let us wrap up by reviewing the key takeaways from today's lecture. First, we learned that Darboux integrability focuses on trapping the true area between strict upper and lower boundaries. Second, Riemann integrability focuses on taking random samples within small slices. Finally, the sandwich theorem proves that for any well-behaved function, these two methods are two sides of the same coin, always converging to the exact same value. You have now mastered the absolute bedrock of how we understand the area under a curve. Great job today.